So it all came to life in a dark bar in Madrid. I encountered my colleague from McGill, Michael Meany. And we were drinking a few beers, and like scientists do, he told me about his work. And he told me that he is interested in how mother rats lick their pups after they were born. And I was sitting there and saying, this is where my tax dollars are wasted, on this kind of soft science. And he started telling me that when the rats, like humans, lick their pups in very different ways. Some mothers do a lot of that. Some mothers do very little, and most are in between. But what's interesting about it is that when he follows these pups when they become adults, like years in human life, long after their mother died, they are completely different animals. The animals that were licked and groomed heavily, the high licking and grooming, are not stressed. They have different sexual behavior. They have different way of living than those that were not treated as intensively by her mother. So then I was thinking to myself, is this magic? How does this work? As geneticists would like you to think, perhaps the mother had the bad mother gene that caused her pups to be stressful, and then it was passed from generation to generation. It's all determined by genetics. Or is it possible that something else is going on here? So in rats, we can ask this question and answer it. So what we did is a cross-fostering experiment. You essentially separate the litter, the babies of this rat at birth, to two kinds of fostering mothers. Not the real mothers, but mothers that will take care of them. High-licking mothers and low-licking mothers. And you can do the opposite with the low-licking pups. And the remarkable answer was, it wasn't important what the gene you got from your mother. It was not the biological mother that defined this property of these rats. It is the mother that took care of the pups. So how can this work? I'm an epigeneticist. I'm interested in how genes are marked by a chemical mark during embryogenesis, during the time we're in the womb of our mothers, and decide which gene will be expressed in what tissue. Different genes are expressed in the brain, and in the liver, and the eye. And we thought, is it possible that the mother is somehow reprogramming the gene of her offspring through her behavior? And we spent 10 years, and we found that there is a cascade of biochemical events by which the licking and grooming of the mother, the care of the mother, is translated to biochemical signals that go into the nucleus and into the DNA and program it differently. So now the animal can prepare itself for life. Is life going to be harsh? Is it going to be a lot of food? Are there going to be a lot of cats and snakes around? Or will I live in an upper-class neighborhood where all I have to do is behave well and proper, and that will gain me social acceptance? And now one can think about how important that process can be for our lives. We inherit our DNA from our ancestors. The DNA is old. It evolved during evolution. But it doesn't tell us if you are going to be born in Stockholm, where the days are long in the summer and short in the winter, or in Ecuador, where equal number of hours for day and night all year round, and that has such an enormous amount on our physiology. So what we suggest is perhaps what happens early in life. Those signals that come through the mother tell the child what kind of social world you're going to be living in. It's going to be harsh, and you better be anxious and be stressful, or it's going to be an easy world, and you have to be different. Is it going to be a world with a lot of light or little light? Is it going to be a world with a lot of food or little food? If there's no food around, you better develop your brain to binge whenever you see a meal, or store every piece of food that you have as fat. So this is good. Evolution has selected this to allow our fixed old DNA to function in a dynamic way in new environments. But sometimes things can go wrong. For example, if you're born to a poor family, and the signals are, you better binge, you better eat every piece of food you're going to encounter. But now we humans in our brain have evolved, have changed evolution even faster. Now you can buy a McDonald's for $1. And therefore, the preparation that we had by our mothers is turning to be maladaptive. The same preparation that was supposed to protect us from hunger and famine is going to cause obesity, cardiovascular problems, and metabolic disease. So this concept that genes could be marked by our experience, and especially the early life experience, can provide us a unifying explanation of both health and disease. But is it true only for rats? The problem is we cannot test this in humans, because ethically we cannot administer child adversity in a random way. So if a poor child develops a certain property, we don't know whether this is caused by poverty or whether poor people have bad genes. So geneticists would try to tell you that poor people are poor because their genes made them poor. Epigeneticists will tell you poor people are in a bad environment or an impoverished environment that creates that phenotype, that property. So we moved to look into our cousins, the monkeys. My colleague Stephen Sumi has been rearing monkeys in two different ways. Randomly separated the monkey from the mother and reared her with a nurse in a surrogate motherhood conditions. So these monkeys didn't have a mother, they had a nurse. And other monkeys were reared with their normal, natural mothers. And when they were old, they were completely different animals. The monkeys that had a mother would not care about alcohol, they were not sexually aggressive. The monkeys that didn't have a mother were aggressive, were stressed, and were alcoholics. So we looked at their DNA early after birth and see, is it possible that the mother is marking? There is a signature of the mother in the DNA of the offspring. These are TA14 monkeys, and what you see here is the modern way by which we study epigenetics. We can now map those chemical marks, which we call methylation marks, on DNA at a single nucleotide resolution. We can map the entire genome. We can now compare the monkey that had a mother and not. And here's a visual presentation of this. What you see is the genes that got more methylated are red. The genes that got less methylated are green. You can see many genes are changing, because not having a mother is not just one thing. It affects the whole way. It sends the signals about the whole way your world is going to look like when you become an adult. And you can see the two groups of monkey extremely well separated from each other. How early does this develop? These monkeys already didn't see their mother, so they had a social experience. Do we sense our social status even at the moment of birth? So in this experiment, we took placentas of monkeys that had different social status. What's interesting about social rank is that across all living beings, they will structure themselves by hierarchy. Monkey number 1 is the boss, monkey number 4 is the peon, and you put 4 monkeys in a cage, there will always be a boss and always be a peon. And what's interesting is that the monkey number 1 is much healthier than monkey number 4. And if you put them in a cage, monkey number 1 will not eat as much, monkey number 4 will eat as much. And what you see here in this methylation mapping, a dramatic separation at birth of the animals that had a high social status versus the animals that did not have a high status. So we are born already knowing the social information. And that social information is not bad or good. It just prepares us for life, because we have to program our biology differently if we're in a high or the low social status. But how can you study this in humans? So we can't do experiments, we can't administer adversity to humans, but God does experiments with humans. And it's called natural disasters. So one of the natural disasters, the hardest natural disaster in Canadian history, happened in my province of Quebec. It's the ice storm of 1998. We lost our entire electrical grid because of an ice storm when the temperatures were in the dead of winter of Quebec, -20 to -30, and there were pregnant mothers during that time. And my colleague Suzanne King followed the children of these mothers for 15 years. And what happened was that as the stress increased, and here we had objective measures of stress, how long you were without power, where did you spend your time, was it in your mother's-in-law apartment or in some posh country home? So all these added up to a social stress scale, and you can ask the question, how did the children look like? And it appears that as stress increases, the children develop more autism, they develop more metabolic diseases, and they develop more autoimmune diseases. And we would map the methylation state, and again you see the green genes becoming red as stress increases, the red genes becoming green as stress increases, an entire rearrangement of the genome in response to stress. So if we can program genes, if we are not just the slaves of the history of our genes, but they could be programmed, can we deprogram them? Because epigenetic causes can cause diseases like cancer, metabolic disease, and mental health diseases. Let's talk about cocaine addiction. Cocaine addiction is a terrible situation that can lead to death and to loss of human life. We ask the question, can we reprogram the addicted brain to make that animal non-addicted anymore? We used a cocaine addiction model that recapitulates what happens in humans. In humans, you're in high school, some friends suggest you some cocaine, you take cocaine, nothing happens, months pass by, something reminds you of what happened the first time, a pusher pushes cocaine, and you become addicted, and your life has changed. In rats, we do the same thing. My colleague Alia did. He trains the animals to get used to cocaine, then for 1 month, no cocaine, and then he reminds them of the party when they saw the cocaine the first time, by cue, the colors of the cage when they saw cocaine, and they go crazy. They will press the lever to get cocaine till they die. We first determined that the difference between these animals is that during that time when nothing happens, there's no cocaine around, their epigenome is rearranged, their genes are remarked in a different way, and when the cue comes, their genome is ready to develop this addictive phenotype. So we treated these animals with drugs that either increase DNA methylation, which was the epigenetic mark we look at, or decrease epigenetic markings. And we found that if we increase methylation, these animals go even crazier. They become more craving for cocaine. But if we reduce the DNA methylation, the animals is not addicted anymore. We have reprogrammed them. And the fundamental difference between an epigenetic drug and any other drug is that with epigenetic drugs, we essentially remove the signs of experience. And once they're gone, they will not come back unless you have the same experience. So the animal now is reprogrammed. So when we visited the animals 30 days, 60 days longer, which is in human terms, many years of life, they were still not addicted by a single epigenetic treatment. So what we learned about DNA, the DNA is not just a sequence of letters, it's not just a script. DNA is a dynamic movie. Our experiences are being written into this movie, which is interactive. You're like watching a movie of your life with the DNA with your remote control. You can remove an actor and add an actor. And so you have, in spite of the deterministic nature of genetics, you have control of the way your genes look like. And this has a tremendous optimistic message for ability to now encounter some of the deadly diseases like cancer, mental health, with new approach looking at them as maladaptation, that if we can epigenetically intervene, reverse the movie by removing an actor and setting up a new narrative. So what I told you today is that our DNA is really combined of two components, two layers of information. One layer of information is old, evolved for millions of years of evolution. It is fixed and very hard to change. The other layer of information is the epigenetic layer, which is open and dynamic and sets up a narrative that is interactive, that allows us to control, to a large extent, our destiny, to help the destiny of our children, and to hopefully conquer disease and serious health challenges that have plagued humankind for a long time. So even though we are determined by our genes, we have a degree of freedom that can set up our life to a life of responsibility. Thank you.